Good afternoon, everybody. Welcome to our Sunday Space Show program. I'm your host, David Livingston in Las Vegas, and thank you all for joining us. A couple of very quick announcements before I introduce our guest. They are that Jason Andrews is back with us on Tuesday, and Doug Messier is doing Hotel Mars with us on breaking down what NASA is doing with Artemis and attempting to go to the moon and maybe putting nuclear power on Mars and uh, who knows what else. Friday, the former editor of Astronomy magazine, his name is David Eicher, is coming on the program. And Sunday is no show for Easter Sunday. So that's what we have coming up. And Dr. Joel Sercel is back with us today. So he is the CEO of TransAstra, but he also has a long track record of being involved with government and NASA and other kinds of space programs. He has a great education. He's got his PhD and master's in mechanical engineering from Caltech. He did a PhD dissertation in plasma physics from my alma mater at the University of Arizona in Tucson. And as I said, he's been a guest on the program before. We're happy to have him back. And Joel, welcome back to the space show, not using telephones anymore, but going to this Zoom and a more of a video sort of panel
Nice.
conference program. And we're glad to have you. And since we're on Substack and YouTube and Vimeo and other places, why don't you introduce the public at large to TransAstra? Why did you start it? What is the need? What's the business model? How do you hope to get revenue? Um, my background is all from the business side. So just kind of, if you were talking to someone at Bloomberg or something, they want to know how you make money and, why you're doing this or that. That's kind of the introduction I'm after.
Well, sure. I started TransAstra uh, almost 10 years ago, but actually a little more than 10 years ago. Um, After asking my question, what's the most important thing you could do for the future of life from Earth? And I have believed for decades that the answer to that question is develop the enterprises that are needed to harvest the resources of space for humanity and its progeny as we spread throughout the solar system. So um, that's that's why I founded TransAstra. Why did I found it 10 years ago? The reason I founded it 10 years ago is because it became clear about 10 years ago that the vision of the exciting future in space that I thought we would have had by the 1990s when I was a kid, growing up in the 60s and 70s, um, is going to happen. And uh, my background is that I, I I did a degree in engineering physics at the University of Arizona in the early 80s. And it was my plan at that point to start a company, entrepreneurial company, to build solar thermal rocket upper stages to take payloads from the space shuttle to GEO and other destinations. People said, well, my advisors said, well, don't do that. You don't have the experience. Go to JPL for a while because I had a nice job offer from JPL. Get some experience and then do that. So I did that. And I had a nice little career at JPL where I did every job at JPL. But I became convinced over the years that NASA and JPL were not part of the solution because what we need is sustainable activities in space. And what I mean by sustainable is they have to be economically sustainable, not on the backs of the taxpayers, which means you have to have a way to make a profit and a product that someone's willing to pay for in space. Once that happens, then the exponential future that we're for will happen in space. Um, so around the turn of the century, I left JPL and uh, went to Caltech, where I was the director of a lab at Caltech, and I made most of my living consulting, contract engineering, and that sort of thing. And I was kind of, after a while, I for a few years I took a senior government job for on a big classified communication satellite program for the Air Force. But that really turned me off on government in space, and I just never thought I would see inefficiency like that in my life. Um, and I really got disenchanted with space. And I grew up. Um, I graduated from college in the early 80s, so that places my age. I grew up during the time when the space shuttle was the big promise for the future, and it was going to give us low cost, reusable access to space. And one of my early mentors was Gerard O'Neill from Princeton, who really was the first one who really asked, what's the right place for people to live? And the answer is not on the surface of planets. It's in worlds made in space out of the resources of asteroids and moons. But the problem is, in order to make that happen, you have to have a robust industry in space. You have to have a way to make money in space. And you need low cost, reusable access to space. And the space shuttle was an abject failure in that. It was reusable in a refurbishable sense, but it was never affordably reusable, and it was never routine, and it was never safe. And so for 30 years, NASA kept doubling down on this contraption, applying all kinds of great engineering skill to make something that was architecturally not sound try to work. And it set the space program back 30 years. And so, in the late '00s and early teens, I was making my money as a contract engineer, management consultant, trainer. And I got a consulting gig to an agency of the government on the US, on the East Coast, that was looking to buy rockets. And they were looking at, should we buy SpaceX rockets? This is around the time of Falcon 9 launch 1, 2, 3, roughly. And all of the senior advisors and all the graybeards and all the wise people around the Air Force and the DoD said, absolutely don't buy SpaceX rockets. They're never going to be reliable. They don't have good engineering processes. And it doesn't make any sense to put $1 billion satellite on a $50 million rocket. You should put $1 billion satellite on a $1 billion rocket. Um, uh, uh, and so some people on the East Coast knew that I had experience in Silicon Valley, that I knew the space business, that I knew Elon, I knew Gwen from work I'd done with them before. So they asked me to go in and kick the tires on the company. And I was very lucky to work with a small group of hand-selected consultants to really evaluate SpaceX's engineering processes and that sort of thing. And I came away from it realizing that the dreams of my youth were going to come to fruition, that we were going to have low-cost access to space. That was going to open up all kinds of business models. And the time to get going was now. So I wrote, so I started to think about, well, what's the most important thing you could work on? And the answer is asteroid resources. And I asked myself, well, what does it take to solve the problem of harnessing asteroids to build things in space? And the answer came, first of all, you have to have low cost access to space, but you have to have a lot of other things that other people were working on. But what were the things that no one was working on effectively that needed to happen? And it came down to what I call the 4 problems. And those 4 problems are detect, capture, move, and process. So detect is about finding the very small asteroids that have very low delta Vs from the Earth that can be cost effectively harnessed. So it's better telescope technology. Capture is you can't land on an asteroid. To work with it, you've got to capture it in some kind of an enclosure. Move is better propulsion technology. My PhD was in plasma physics and space propulsion. And I've always felt as though the real critical problem in space exploration and development is propulsion. And then the last one is process. How do you process asteroid materials into things that are useful and valuable in space? So I started to invent a bunch of solutions to those problems. And I looked around for where I could get funding. And I heard about this program in NASA called NIAC, the NASA Innovative Advanced Concepts Program. And so I started writing proposals to NIAC around solving these problems with an eye towards harnessing the resources of space for humanity. And lo and behold, I started winning proposals, which I was really delighted about. And I felt pretty lucky for because NIAC is about the most competitive program in NASA. And I think I became the first 7-time NIAC fellow. So when you win a NIAC grant or contract, it's a fellowship, you become a NIAC fellow. And I became the first 7-time NIAC fellow and the most winning NIAC fellow, the NIAC fellow who got the most money from NIAC. It was almost $4 million. And so with that, I was able to found TransAstra and scale it for the first few years. I ran TransAstra out of this chair, and the experimental and hardware work was done by my friends in universities. So our university network has always been a really core part of what NIAC, what TransAstra is from day one. So we've worked with universities like the Colorado School of Mines, the University of Hawaii's Institute of Astronomy, the University of Central Florida and their Center for Lunar and Asteroidal Surface Science. Purdue, half of the employees, a quarter of the employees at TransAstra have been from Purdue over the years, and Virginia Tech. And so we scaled the company, solved a lot of these fundamental technology problems associated with asteroid mining, patented them. And then by about 2020, it became clear that we were mature enough to go after venture funding. So we went through an elite tech incubator in Silicon Valley called, sorry, it's Sunday morning. Last night I was up late. But we went through Y Combinator, which is an elite incubator in Silicon Valley. Y Combinator companies are worth about $1 trillion in total so far. Includes things like Airbnb, Uber, Relativity, and then Stoke, many companies that you've heard of. So we went through Y Combinator, raised about $6 million there, and started to hire people, got a facility, started to scale the company. And then over the last 5 years, we've won about 15 or $16 million in contracts from NASA, the Space Force, and other government agencies. Some of the government agencies we work with don't like us to talk about them, so we just say other government agencies. And we've raised a total of about 16 million in venture funding. And we've flown hardware in space. We own and operate a small global network of telescopes, which we think are the most sensitive, cost-effective telescopes for finding and tracking faint moving objects in deep space. So things are going well. It's very exciting. So was that too long-winded of an answer to your question, David?
No, it opens the door to a couple of my questions, and also I have an email from a listener who could not be with us. But are you close to operational revenue, and what is the actual product or service?
Yeah, so we are, as I said, we've made about $16 million in revenue over the past few years. And we have executed about 24 contracts from NASA, the Space Force, the Air Force, and other government agencies. We are still we're still significantly venture funded, and we use that venture funding to do R&D and to help us scale to bigger and better things. But the thing about those 4 problems, detect, capture, move, and process, is that each one of them has applications outside of asteroid mining. So with detect, we've invented what we call the Sutter telescope systems. And on the ground, we have our Sutter TKO, which is turnkey observatory system. People can go to the website, transastra.com, to learn about the Sutter TKO system. But it's a highly modular, low cost, sophisticated telescope that we can observatory system that we can reproduce very inexpensively. And we now own and operate telescopes in Spain, California, Arizona, and Australia. So we now have operated telescopes at 5 observatory sites. And it's a really unique telescope design where we use low-cost commercial off-the-shelf optical tube assemblies, what most people call a telescope, aggregated together as compound telescopes because it's cheaper to buy several small ones than one big one. And we add the apertures together digitally. And we have special software that helps us find things that when they move in space, the way asteroids do, long exposures don't work for finding faint moving objects in space because you don't know where they are. But we use software to do that very powerfully and more cost effectively than anyone else. And so the Space Force pays us to build and operate those telescopes for them. And that is a going business line that we have in the company. And in fact, next week when Artemis launches, we'll be tracking it with our global telescope network, and we'll be doing that as part of our normal operations that we do for the Space Force. And with these telescopes, you can see something the size of a washing machine easily at lunar distances. In fact, the Chinese had a spacecraft that was going to the moon, and it had sub-satellites drop off before it got to the moon. And we were the first ones to see that. And that was not expected in the West, that they would drop off before they got to the moon. That was a significant finding and shows the power of our low-cost commercial solutions. Capture bag, we developed the capture bag for capturing and controlling asteroids. But what we found at customer request is that it can be scaled to all different sizes and in different geometries. So we've built capture bags that are small enough to go in a 1U enclosure, which is about the size of a coffee cup. Deploy a capture bag that can capture a CubeSat. Or we are currently building and flight qualifying for NASA a 10-meter capture bag. It's big enough to capture a 150-ton asteroid or most of the satellites that are up in space and geo and so on. And we're designing and building that right now. We'll be testing it in the high bay at JPL. We have great friendship and partnership with JPL. And we'll be doing that this summer. And that is actually big enough to go out and start getting asteroids with. And NASA really is excited about us doing that, our sponsors in NASA. And there are customers that are anxious for us to use that for end-of-life disposal of satellites in low Earth orbit, as well as cleaning up navigational hazards in GEO, MEO, and other places. The watchword here is dual use. It's dual use for civil and defense purposes. And then it supports the longer term, but not very long term mission of asteroids. It's going to happen a lot faster than people think.
Let me read you this question, and then the dream team with the space show can enter in. This
Nice.
is from Dr. Doug, and he's a medical doctor in Southern California around Loma Linda area. Given that NASA and SpaceX are looking at landing on the moon and Mars, where there are enormous quantities of material right there, and with plans to have people in bases overseeing the processing of that material, how can the usage of asteroid material be competitive compared to those of other sources?
Yeah, so the problem is, how do you make money on the moon or Mars? So for example, something that we've been talking about for several years now is data centers in space. So it makes a huge amount of sense to move data processing, large-scale data processing, especially things like crypto and AI training into space, because it's a power-intensive process that consumes a lot of resources on the ground. And power is becoming cheaper in space than on the ground. But if you have two if you have two companies that are competing to build cost-effective data centers in space, and one is building those data centers on the ground and launching them up into space, the cost of that launch starts to be prohibitive, even with low-cost systems like the Starship. Whereas if we're harvesting the material to build those data centers from near-Earth asteroids and harvesting the rocket propellant to deliver them to their operational orbits from asteroids, it becomes vastly less expensive. So, Elon says that he's going to build his data center factory on the surface of the moon, but then he has to launch those data centers up from the surface of the moon on mass drivers. And it will cost billions and billions of dollars to build mass drivers to launch things up from the moon. And it's really hard to land on the moon, and it's expensive to land on the moon, and the same with Mars. So I want to clarify a misconception about asteroids. So we're all taught in school that the asteroids reside in a belt between the orbits of Mars and Jupiter. That's a lie. That's not true. The asteroids form a cloud around the sun that's grazing the surface of the sun at just 4 solar radii. From just grazing the surface of the sun at a few times the radius of the sun away are asteroids. They spiral into the sun and they break up when they get closer than about 4 solar radii due to heating. And they extend all the way out to the Oort cloud. Now, that's important. And for asteroids of engineering scale that you can work with normal size equipment, not mountain size asteroids, but engineering scale asteroids, there are billions of asteroids. Now, and of those billions of asteroids, to start with, there's a tiny sliver of them constituting a tiny amount of material, only about 1 million metric tons, that we're interested in the short term. And this 1 million metric tons of asteroids are a few hundred asteroids that are in what we call highly Earth-like orbits around the sun. So the way to think about this is the Earth goes around the sun in a nearly circular orbit with a zero inclination by definition. That's what the Earth's plane of orbit around the sun constitutes the plane of the ecliptic. But if you're in a nearly circular orbit at a low inclination, you're in a highly Earth-like orbit. Well, there are probably 200 to 300 asteroids ranging in size from a few meters to a few tens of meters in that highly Earth-like orbit. And what's really interesting about these asteroids in highly Earth-like orbits, and this is a population that the science community doesn't study very carefully. I think TransAstra knows more about this population than anyone else, is that the rocket propellant required to get to those asteroids and get resources back from them is less than any other location in the solar system. Vastly easier to get to than the moon for the purposes of resource utilization. And it's these small asteroids in highly Earth-like orbit that represent the first bonanza of the space gold rush. We named our Sutter telescopes after Sutter's Mill, where they discovered gold in California, because the key to the gold rush to space is finding these resources in unique locations. And it's these asteroids in highly Earth-like orbits that are so exciting. Now, these asteroids are basically going around the sun in an orbit just like the Earth's orbit around the sun, plus or minus 1% or 2. And they drift by the Earth very slowly. An astronomer would say they have a synodic period of about 20 years. That means a typical asteroid would either drift faster than the Earth or slower than the Earth at a rate of about 1/20th of a trip around the sun, different than the Earth every year. So it takes about 20 years, maybe as little as 10 or 15 years and as much as 40 or 50 years for them to come back and pass by the Earth. But when they pass by the Earth, they're going very slow, a few hundred meters per second. Now, here's a weird and strange thing about astrodynamics that even people who know about astrodynamics will find surprising. And that is, if I have a rocket and I want to launch my rocket out to infinity from the Earth, to the top of the Earth-Moon gravity well, where these asteroids are just drifting by. It actually takes less rocket propellant for me to get my spacecraft to that spot than it does to get to GEO, and much less than to get to the orbit of the moon around the Earth, and much, much less than to land on the Earth, on the moon. The delta V to get to these targets is much less than any of these other locations. And there's 1 million tons of resources energetically at that location, and we can go out and get it. And that's the key to the beginning of the gold rush to space.
What is the? Go ahead, John. You can do it, and then I'll ask my question in a few minutes.
Yeah, Joel, you talked about using the capture bag for debris orbital debris
Yep.
removal.
Yep.
On your website, you said that cleaning orbital debris would be 40% faster using your capture bag, and I think you're using your technology to recycle those resources. Do you use your optical mining technology to process satellite resources and reuse them? How does that work?
That's the hope. So if you look at the technologies, remember I said the four problems that we have to solve are detect, capture, move, and process. The fourth one is process. The materials processing technology that you need to extract useful resources from asteroids is pretty much the same technology that you need to recycle orbital debris and defunct spacecraft. And we have a number of patents in that area. And it's pretty straightforward technology. It's not mysterious. But work does need to be done on it. When you think about materials processing at large scale in space, you do it in very different ways than you do materials processing on the ground. On the ground, you typically have water, lots of electric power, gravity, and atmosphere. And those all fundamentally affect how you do chemistry, material processing, that sort of thing. In space, you take advantage of the space environment. You have cheap and plentiful vacuum. You have copious solar power, which you can very easily, with low-tech reflectors, concentrate to extreme levels to produce very high temperatures. You have access to the cold of space, but it has to be done through radiant cooling rather than convective cooling. And you can take advantage of microgravity. So all of our material processing technologies take advantage of those unique properties of space and work in very different ways than terrestrial materials processing. And when people who aren't schooled in this area think about, oh my gosh, how could you ever smelt metal out of an asteroid, or melt a spacecraft to recycle its material? And they think, and you think about how you would do it on the ground, and could you ever do that in space? And it seems like a prohibitively difficult problem. But I'm not going to get into the details of the proprietary methods and systems. But what I'll say is, people figured out how to smelt metal out of rocks on the Earth 3,000 years ago. It's not that hard. And clever people who understand chemistry and materials processing, and innovative engineers who knows how to take advantage of the vacuum of space and the thermal energy from solar concentrators, can come up with really good ways to do it at very low cost.
So just one more question. Sorry.
Sure.
If these satellites or the asteroids are tumbling, how do you deal with that to eliminate that movement of the objects that you're capturing? Do you introduce a gas to slow them down, or how does that work?
No, it turns out that there's an upper limit to how fast asteroids tumble. Some of them may be tumbling too fast for us to handle, but at reasonable rotation rates, we can capture them with the capture bag. And depending on what exactly the object is, like say this is the asteroid, and it's typically an object in space will be tumbling around its, not tumbling, spinning around its principal axis. What we do is we make the bag bigger than the extent of the object. And we can do that with relatively low mass because these bags are made of very tough, thin film materials. Bag opens up and it's held open by inflation gas pressures in struts and ribs that we build into the bag. Um, and uh, in, and so it's contained in a very tight enclosure, fold up like an origami folding. Then it has a canister that opens. By the way, it's vacuum packed into its container before it's launched into space because we don't want residual gas to blast the thing out of the canister. And we demonstrated that our vacuum packing works in our flight at ISS in October. I don't know if you guys saw the video of our capture bag demonstration on the space station last fall, but it was a big success. I can talk about that in a minute. But what you do is you open up the capture bag and then you fly to the target. And if the target is tumbling, you match its principal rotation axis, kind of like in the movie 2001: A Space Odyssey. And then in that rotating frame, you fly the bag over the object. Now, this is an important distinction. Some people say, well, we're going to clean up orbital debris with precision robotic arms or grappling mechanisms. That requires precision docking. That's a much more expensive process. And it works really well if you're docking with the space station. That's a cooperative target. What if it's a non-cooperative target, a broken spacecraft or a tumbling asteroid? It's not doing anything to help. So what you really want to do is you don't want to do a precision dock. You want to do a loose rendezvous and more like a berthing maneuver, but you're not actually attached to it. And in that rotating reference, then you close the end of the bag so the object can't get out. And then you cinch the bag down. Now, the bag is controlled with lanyards that are inside the bag. We've demonstrated this all dozens of times in our laboratory and in space. We can close the bag and open it, and we can pull on that bag. And the typical lanyard strength is a tensile strength of maybe 200 pounds. And we can pull very hard and cinch that object down to the spacecraft. Once we've got it under positive control and cinched it down, then we use the attitude control of the space system on the spacecraft to detumble it. People say, well, if you've got a 100-ton asteroid, you can't detumble that. Well, people say that when they haven't run the numbers. So it turns out that at the typical rotation rate of 1 RPM, say 100-ton asteroid, it only takes a few hundred kilograms of propellant to detumble it, as long as your thrusters are on reasonable moment arms. And for a tumbling spacecraft, it's well within the attitude to control capability of a typical carrier spacecraft that we work with.
Very cool. Thank you.
Marshall?
Yeah, my question is, we have a general idea of the mix of metal, electronics, et cetera, for objects in space. But what about the near Earth orbital objects? Are there enough of a mix that you can pick and select so that you end up with the proper ratio of metal and silicon dioxide and copper and gold to make something useful?
It's a really good question. We have a really good idea of what these objects are made of. And a big part of the reason that we have a really good idea of what these big objects are made of is because we send a lot of people to Antarctica all the time.
Oh, yes.
So if you pick a rock in Antarctica, it came from space. And so I think NASA and the science community in the United States have 20,000 meteorite samples from all different kinds of meteorites. And there are taxonomies of meteorites. And each different taxonomic type is made of different kinds of things. And some don't fit into clear taxonomies, but most of them do. And we can look at the meteorites that we pick up and we know what their optical properties are. We know their their color spectrum and that sort of thing. And then astronomers can look at asteroids out in space and do a spectroscopy on those asteroids. And they have a taxonomy of the asteroids out in space. And we can map the asteroid taxonomies to the meteorite taxonomies. And so, so we know, for example, that typically in the NEO population, about 1 in 4 to 1 in 5 asteroids is what we call a carbonaceous chondritic type asteroid.
Mhm.
These are also known as CIs and CMs in different vernacular. And they're about anywhere from 5 to 30% water, typically in the 15% water range. So they're also loaded with carbon
Mhm.
and sulfur. And so these are the ingredients that you need to make rocket propellant.
Mhm.
And then about 1 in 20 are type M or type X asteroids that are full of metals. And we know exactly and we know, when I say we have very good mathematical models of the statistical distribution of the materials in each of these types. So if I say we know exactly what they're made of, what I mean is statistically we can characterize what they're made of and what the uncertainties are and what they're made of. So for example, people talk about platinum group metals in type M asteroids. Well, it looks like there's the platinum in type M asteroids is a little higher in concentration than the platinum in platinum ores on the Earth. So if you had a 100-ton type M asteroid, 100-ton would be about the size of this room. It's worth about $1 million in terms of all the different metals here on the Earth. So it probably doesn't make sense. We don't think it makes sense to go out and get that material and bring it back to the Earth because we think it's going to cost more than $1 million to go and process a 100-ton asteroid in space. But that 100-ton asteroid will be worth billions in space to make things out of in space to avoid launch costs.
Mhm. You kind of touched on the point of water and oxygen being in many of the asteroids. What about rare earth elements that
Yeah, that's
are
what I was
used
just
for
talking
the
about.
electricity?
Yeah, that's what I was just
Are
talking
they
about.
there?
Yeah, they're there, and we know their concentrations, and we will need those to make data centers and space
Mhm.
habitats, space hotels, and swarms of communication satellites and Earth observing satellites and capital ships for the Space Force. All the engineering materials that we need are in the asteroids. The one thing that there isn't much of, which is a bit of a problem, is nitrogen.
Yeah.
Ryan,
So
go ahead. Did you want to finish, Joel, or Ryan wants to ask you something?
no, so David, you go ahead and tell me which questions to answer.
Ryan, go ahead.
Cool. Yeah, great. Thank you. Yeah, so in the recent Ars Technica piece about TransAstra and specifically the New Moon project, in the artist's depiction, the image in the article, it shows TransAstra, I guess, assets, but then there's also a kind of a structure there, a structure, trusses and supports and so forth, sort of building out like this New Moon research facility. And so my question is then, are you looking at building that? Do you have projects to do robotic construction space? Or is that going to be provided by I guess, the unnamed collaborator on the New Moon project?
So we conceived of New Moon on investor resources some time ago. And our concept, which is a couple of years old, is to go out and get the first asteroid from this highly Earth-like population and bring it into the Earth-Moon system at a region that we call the rim. And then build reusable craft that can do that over and over again, hundreds of times in the 2030s, to aggregate as much as 1 million tons of material. How much is 1 million tons of material? Think of it as 10 supercarriers. So it's a lot of material. It's small by large-scale industrial standards on the Earth, but it's the beginning of a trillion-dollar space industry. And we think that it's the easiest way by far to get the first 1,000,000 tons of material for space industrialization. By the way, I also think the moon is a great source. I also think the Martian moons are a great source. Well, one place I don't think is any source for anything useful is the surface of Mars. It has no economic value because it's a long way away. It's hard to get down to the surface. Once you get to the surface, you have to come back from the surface. And it's got every disadvantage and any advantage. If we wanted to harvest materials from the surface of planets, we would do it from the Earth. But the Martian moons may be interesting, just because less gravity. They're easier to get to and from. There are advantages, and they also have all the materials, many of the materials that you need for space industrialization. Sorry, I'm off topic, but the concept here is to build what we call the solar forge. This is the TransAstra concept that we produced on our own a long time ago. The solar forge comprises these 3 material processing technologies that we call optical mining. That's for grinding up asteroids using selective grinding machines and extracting the volatile materials. Vapor phase fractional distillation, which is vaporizing the engineering materials out of the asteroids and then depositing them at each at their own deposition site using temperature as a sieve. But then some engineering materials would want to deposit at the same temperature. So we separate those with a patented, I don't know if it's patented or patent pending process that we call quantum spin separation. That's based on the physics of the Stern-Gerlach experiment. And we haven't found any engineering materials that can't be separated by a combination of vacuum phase fractional distillation and quantum spin separation. Basically, every atom has a different magnetic moment, every unique atom type. And so if you let them drift at thermal velocities through a magnetic field in vacuum, they'll deflect differently. And every set of engineering materials that we found that deposit at the same temperature have different net magnetic moments, so they can be further separated with quantum spin separation. So whether or not we build that with other partners or do it on our own with investor funds is TBD.
Cool. Thank you.
AJ?
Yeah, hi. My question, I'm trying to understand the delta V, the numbers that you mentioned. Now, I'm assuming that when you say that the delta V to get to the asteroid, etc., is very, very small, that is because you are already in space.
Nope.
And because the gravity well of the Earth, otherwise, for every one of these things that you may build, obviously requires 10 kilometers per second just to get out to the LEO, and 3 or so more to get to the asteroid.
Yeah, so what I'm saying is, once you're in LEO,
yeah.
So these asteroids in highly Earth-like orbits around the sun are moving at very low relative velocities to the Earth.
To Earth, right?
In heliocentric space.
Yes.
Maybe as little as tens of meters per second to as much as at the most of a kilometer per second or so.
Mm-hmm.
Okay, so let's say that I was going to let's say that I'm in low Earth orbit.
Mm-hmm.
I guess from your perspective, low Earth orbit,
mm-hmm.
and I want to get out to GEO. How do I do that? With the
No,
standard home and transfer, I do a perigee burn, and that perigee burn is almost enough to get to me to infinity, just a little bit less.
Yes.
That takes me out on elliptic, and then I do an apogee burn to circularize. Well, if I look at the magnitude of those 2 delta Vs, and I compare that to the delta V as I'm in low Earth orbit, I do a perigee burn, and I want to go to infinity. It's only slightly more than the first burn, but the way you get to infinity is you go to infinity and you coast to a stop.
Yeah.
And so the delta V to get to the top of the gravity well is actually less than the delta V to get to GEO. Same thing if I'm going to the moon. Let's say I wanted to get to the moon's orbit around the Earth. It's the same thing. I do a delta V to depart LEO, and then I have to do a circularization delta V when I get to the moon. Now, if I want to actually go into orbit around the moon, there's another delta V. And if I want to land on the surface of the moon, there's another delta V. When you start to add up all those delta Vs, the delta V to get to these targets as they come drifting by the top of the gravity well in the region of space that we call the rim, which is a region that is near the edge of the Hill sphere. So the Earth and the moon are not in charge gravitationally, but neither is the sun, because we're not far enough away from the Earth-Moon. And the other planets like Jupiter and Mars can actually affect your trajectories. That region we call the rim. The delta V to get to the rim is less than the delta V to get to GEO, lunar distant retrograde orbit, Earth-Moon L1, Earth-Moon L2. All those delta Vs are harder than to get out to the rim. Once you get to the rim, it's easy to grab those asteroids. And then the thing about being at the rim is it takes relatively low delta V to come dropping down into the gravity well to get to virtually any other orbit. And so if you aerobrake when you go with the atmosphere, it can be very cheap to get to LEO from the rim. So it's a great place to aggregate materials, build factories, build things, and then deliver them anywhere. Now, as far as data centers, the rim is a great place to put data centers because it doesn't have any eclipses, and it's right near the resources that you're making the data centers out of. It does have that couple million kilometers, so several second delta speed of light delay. But for a lot of the data processing tasks, that latency is not a problem. For other data processing tasks, latency is a problem, and they probably want to be in a sun-synchronous orbit close to the Earth.
Yeah, for reaching the rim, of course, I mean, I agree with you that the delta V required to circularize the orbit to go to GEO and perigee and apogee is more than which will be required to go to the rim and reach zero velocity. However, that'll take infinite amount of time or a very large amount of time to get to the rim if your velocity is going to zero.
In theory, it would take forever. In practice, you don't go forever. It takes about 2 months. So one orbit that's at the rim that's very popular is Earth-Sun L2, where the Webb telescope is. Mm-hmm. These typically take a couple of months to get to. Mm-hmm. You can take, with a little more delta V, you can be faster. With a little less delta V, it can take longer. If you've got 6 months, it's a little less delta V. And the other thing you can do when you're on your way to the rim is you can fly by the moon and make it faster and take advantage of those flybys.
Okay.
It looks like, John.
Yeah.
Joe, Alice, go ahead, AJ, and then I'll read the chat question.
Yeah, okay. Another question is, obviously during the Obama administration, they canceled the constellation and installed ARM, I guess, retrieval mission, asteroid retrieval mission, and then asteroid redirect mission. Why did they not? Why did they kind of cancel it afterwards, or why did NASA cancel it afterwards? Was there any other technical reason for that?
There was not really a technical reason. I would say it's a political and programmatic reason and a leadership reason. And that is when the guys who are friends of mine originally conceived the ARM mission, it was to demonstrate high-powered electric propulsion in space. And then NASA got a hold of it and they made it a destination. And NASA was looking for a place to send astronauts to other than the moon or Mars. They thought, well, we'd like to send astronauts to the asteroids, but because of these issues that we were just talking about, that it takes a couple of months to get there and back, Orion can't do it. So they said, well, instead, what we're going to do is instead of bringing Muhammad to the mountain, we're going to bring the mountain to Muhammad. We're going to go out and get the asteroid and bring it to the Earth for the astronauts to have something to do. And in the final analysis, no one could tell what the purpose of the mission was. And then the other thing is, it started off as a JPL mission. I think there was a guy named Steve Olson at NASA Glenn who conceived of this as part of some kind of an IAC proposal. He was involved in a KISS study at Caltech with John Brophy and Fred Kulik. And they had an elegant mission to just go and do the thing. But then they made it a multi-center mission. And every time you make a multi-center mission in NASA, every center takes the full amount of money that the first center would have been able to do the mission for. So the scale of the mission grew and grew and grew. And then the contractors that they had doing it are the usual suspects, and they're very cost effective as long as you're willing to do it for 5 cents, get 5 cents of value on the dollar. And it just started scaling out and became unpolitical. And the basic mission concept, for me, the purpose of the mission is clear: to demonstrate that you can get low delta V asteroids, capture them permanently into the Earth-Moon system as space resources. And that demonstration includes the demonstration of high-powered electric propulsion and capture bags, which are core to it. So to me, it's fundamentally a demonstration of a new capability for space industrialization. As soon as you get very far off of that, you're just confused as to what you're doing. It's like so many things, you got to be clear on the mission. So that's just my opinion. I don't know. I was involved in the mission. I was actually a member of their advisory team. So usually they called the science advisory team, but they called it the FAST. And I can't remember what the FAST stood for, but it was the Science, Technology, and Applications Advisory Team. I can't remember what the acronym was, but we got together several times.
Okay. Electric propulsion you mentioned, was that NEP?
No, actually, NEP really doesn't make any sense technically. It's never competitive with SCP. Nuclear reactors are always much heavier and more expensive than solar panels in space. A typical nuclear reactor in space might weigh 10 to 100 kilograms for every kilowatt of power produced, optimistically. And solar panels are getting down to 3 kilograms per kilowatt. And when you scale, they do fine. So the nuclear power in space is goofy. I don't get it at all. It's that people who really don't understand the engine. What's happened with nuclear power in space is about every 5 to 10 years, a new crew of people who really don't know what they're doing come in, and they're sold on the idea because a bunch of people who want to do the technology sell them on it. They spend a bunch of money and then they cancel the program when sort of adults take over. So I really think this new NASA initiative to send an NEP-powered spacecraft to deliver some helicopters to Mars is goofy. Makes no sense. It would be much, much cheaper if they just did it with solar.
Joe Dallas posted a note wanting to know, it's on the chat, where the rim is, and a couple of questions about the rim, if you can see it there.
Sure. So the rim is a dynamical region in space beyond cislunar space. So historically, cislunar was the area between the Earth and the Moon. And then the area, and then there was a region called translunar, which had a historical definition that went beyond the Moon. But at TransAstra, we use the term Terran space. So Terran space to us is the bubble around the Earth. That's everything inside the Hill sphere out to a little bit beyond the Hill sphere. And then we use the term the rim to refer to the dynamical region where multi-body effects involving more than just the Earth and Moon are important. And that can be as close as the Moon and as far as about 2 million kilometers. And the thing about the rim is it's dynamically very exciting. And we've found some very interesting orbits there that we think will be very important economically and strategically. But I'm not at liberty to talk about those. John Hunt has had his hand up for a long time.
Yes. Yeah, I have a couple of questions here. First of all, since these asteroids are near Earth and in similar orbit, are they part of the asteroids that would pose some threat to Earth itself? There's potential collisions.
Yeah, they could. They could.
Okay.
And by really understanding that population and being able to move them, that's helpful.
Mhm. Yeah. And the second
Um,
thing then is that by processing this stuff, what do we do with the things we don't want to harvest, considering we'd like to get that material so it no longer can be a threat potentially?
well, that's one of the things is when we think about where we would want to put this processing place, we want to put it in an orbit that's very, very safe for a very, very long period of time. That's an important selection criteria. But I don't think there'll be anything that's not useful because you're always going to need radiation shielding in space.
Mhm. So okay, so we'll sort of have kind of a junk pile in space that would be at a safe location, which we can use for various purposes like radiation shielding or whatever.
Yeah, I kind of refer to it as using the whole buffalo. So
Hmm.
if we think about the things that we're going to build in space, the way we think about them on the Earth, where you have these supply chains and you get exactly what you want all the time for everything, that's one way to do it. Another
Hmm.
way to do it is, hey, here are the materials we have. What's the most cost effective way to use these materials to make stuff? Probably make things differently. And if you're launching material up from the Earth to build data centers, then making the chips very rad hard is very important. But if you're making them in space and you've got a lot of radiation shielding just laying around, and we call it slag, you can shield the heck out of it at virtually no cost. That's a plus. So you think
Hmm.
about things differently. And then did Peter have his hand up?
Yes, sir.
I might have my hand up, but Peter.
Okay. Yeah, thank you. So, I got three questions, and please feel free to take whichever direction you want to go. So, not in order of priority. Number one, are you thinking about capture bags? I think you call them fly traps for smaller objects as well, which pose threat
Yes,
to other space items.
yes, 100%. And we're engaged in various different activities that I probably shouldn't talk about because it's proprietary and confidential and all that kind of stuff. But that's absolutely the case. And I think there's a huge commercial market for that.
Okay.
But basically, let's say you're building a satellite constellation and you have to demonstrate that you have a way to dispose of your satellites at the end of the mission. And so what you have to do is carry a lot of extra propellant. But if instead you can say, I'm going to use up all my propellant and then I'm going to have capture bags come along Pac-Man style and clean up every orbital plane at the end, you save a lot of money. And that money saving, the arbitrage on that pays for the missions to do the orbital debris cleanup.
Do
The
you see
other
your,
thing is,
sorry.
even though there are thousands of objects in space now, the orbital debris is really bred mostly by about 50 objects. And if we could just clean up those 50, it would cut the orbital debris environment by a factor of 2. That's very affordable with capture bag.
Do you see your capture bags also handling very small objects like bolts and other small things that pose a threat?
It, it's it's not inconceivable, but it depends on what orbit the bolt is in. It doesn't make sense to send a spacecraft to go chase a bolt if it's got a delta V that's significant from where you are. If it happens to be where you are anyway, then certainly. By the way, like anything else, asteroids are not the solution to all the problems in space. We're still going to need the resources of the moon. Um, capture bag is not the complete solution to the orbital debris problem. There are lots of other important parts of that problem solution.
Thank you. The second question was, you said that you have revenue. Have you actually begun delivering products and services, or is that prepaid revenue against future deliveries? I don't know if you can even speak to that.
Yeah, we deliver things all the time.
Okay.
So we deliver data products to the Space Force on where certain spacecraft that are dark and faintly moving in space are, for example. And the Space Force has paid us to build our TKOs, our TKO in Spain and our TKO in California and Australia.
The last question is maybe you could just give us a big picture of the asteroid capture and asteroid processing industry? Who else is in it? Where are they? Etc. Whatever you could share.
There are 2 or 3 companies that have asteroid in their company vision or plans, and some of them we're friends with all of them, and we think some of their business models are better than others.
Okay, thank you, Joel.
So we respectfully disagree on the business models in some cases, and we agree on the business models in other cases, but we're friends with all of them.
That's great. Thank you.
Bill Swan.
Yeah, so I was wondering if you seem very pragmatic around the costs and things. You talked about nuclear propulsion being a bad idea, which I happen to agree with you on. I was wondering if you'd got some working numbers or developed some working numbers for the cost of sending the factories to the rim, like a per kilogram cost, for example, and what those numbers were and how you arrived at those numbers.
Well, I'm not going to talk about specific numbers or any specific studies that we may or may not be doing or anything like that. But here's what I would say. If you look at a typical exquisite satellite that an organization like JPL or Goddard or contractors that work for the space agency in Chantilly, things like that, that hardware can cost upwards of $1 million a kilogram to design and build. Even the recurring cost. JPL built a radioisotope powered mover that cost $1 billion. And they made a near exact copy of it and still cost a few $1 billion. Okay, so even when they're making multiples. On the other hand, if you look at things like Starlink, and you look at the cost structure for SpaceX, it appears as though the costs are more like $1,000 a kilogram. So about the same as the cost of this or the car that's parked in your driveway. Fundamentally, the cost of something that you make should be, if you make a lot of them, it should be the cost of materials and energy. If you make a few of them, it includes a non-recurring development cost. And non-recurring development costs are very all over the map. When it was costing hundreds of thousands of dollars a kilogram, today's dollars, to put stuff in space, then it made no sense to optimize the cost of the space hardware that you were launching. Instead, you were optimizing the mass of the space hardware you were launching. But that paradigm is changing. So I would say, outside of SpaceX, I don't even know anyone knows how much a Starlink satellite actually costs. But my sense is it's single-digit millions of dollars. So that I think they make them for a cost basis that's comparable to cars. And
I was
so,
thinking more about the launch costs and not the cost of manufacturing the factory. I was thinking like to get to the rim, which is essentially the second cosmological constant, roughly. What are you using for cost numbers for that?
Well, a Falcon 9, what do you think a Falcon 9 fully expendable costs?
Probably like 1.5 or $150 billion, probably.
No. A fully expendable Falcon 9 is $100 million, maybe, or less.
Or did I say billion? I meant million. Yeah. 150. Yeah.
So, but let's say it's 100 million. I'll take your number of $100 million. That's about 5,000 kilograms. That's what it costs now. A factory process in space has to weigh no more than about 2% of its annual output. So you can run the numbers to figure out we're talking about an outpost, a robotic facility that's 100,000 kilograms, something like that. So these are not big billions of dollars. If they are, it's not cost effective. It has to be done on a commercial basis, low cost. So I'm not going to be more specific than that, but anyone can work the numbers.
Well, you're basically thinking using expendable Falcon 9 launch costs to get to the rim, whatever it can get to the rim. You're thinking get 5,000 kilograms to the rim?
So yeah, a Falcon 9 can deliver about 5,000 kilograms to the rim. So
Expendable.
I'm just saying that's what the costs are now, and it's all changing. And as we move forward, we hope to do our first mission this decade. That's been my hope for some time. And I feel as though I can't talk about how or why we think that, but I feel as though we're on track to make that happen. But then we hope to do 100 of these missions, 200 of these missions during the 30s. That we'll use launch vehicles that are available. Transportation is a commodity. Well, if you're looking at shipping something across the country, you hire the cheapest shipper that can get it there in the time that you want. A lot of people think the Starship is going to be the most cost-effective way to get to and from places in space. There may be other vehicles that are more optimized, that are more cost-effective in the 2030s. We'll see. The thing about Starship is that I think LOX methane makes a lot of sense for the first stage. But for the second stage, there's a premium on ISP. And companies like Stoke and Blue Origin use LOX methane first stages and LOX hydrogen second stages, where they have higher specific impulse. That may wind up winning in the reusable rocket race.
Joel, if you mine one of these asteroids to the point of depletion, 100% depletion of resources, I don't know if that's even feasible. What's left of the
Sure it is.
What's left of the
slag? Well, when you show up at the asteroid, what you found was a rock in space. When you're done extracting useful materials from the asteroid, what's left is a rock in space that's made out of different stuff, and it's smaller.
And it's still orbiting and performing like an asteroid?
Exactly. Well, it depends on your business model. We've looked at going out to asteroids, extracting the resources, and then leaving the asteroid in its original orbit and coming back. And we've looked at bringing the whole asteroid back so that we can eat the whole buffalo. Right now, we're leaning towards the eat the whole buffalo regime, like the Ars Technica article talked about. So we think eventually all of that material will be useful. Why? Because eventually humans will live and work in space, and we'll settle space. And when we do, we'll need a lot of radiation shielding, and nothing will be wasted. So here's an interesting factoid that I can leave you with today, because we're coming down to the end.
Right.
If you look at all of the material of the asteroids from near the sun out to the Kuiper Belt, there's enough material to build a 5-meter thick wall with 1,000 times the land area of the Earth. Which means over the next 1,000 years, we can take those walls, make hollow worlds and spin them for gravity, and build worlds with 1,000 times the land area of the Earth. If you include just the moon, there's another 20,000 times that land area. If you start to include the moons of the outer planets and so on, there's hundreds of thousands of times the land area of the Earth available for humanity. Which means that humanity has the potential for an infinite future in the cosmos. Trillions of people and whatever we evolve into living and working in space. We are working the really hard problem right now of the business, the contracting, the engineering, and the physics of making money on that first step of taking us into the cosmos to build businesses in space. Hard-nosed, no kidding, entrepreneurial work. But part of the product that we sell is optimism, because there's not enough people who are keeping in mind the incredible potential of humans. Show of hands for the guys who are here today. How many of you know what the great filter is? So the great filter is one of the answers to the Fermi paradox. Show of hands, how many people know what the Fermi paradox is?
Yeah, we all do that. Yeah.
Okay. So So the answer to the Fermi paradox is either intelligent life is incredibly unlikely, or intelligent life is common, but there's a filter that keeps it from getting to the exponential point. Once we start harvesting asteroids and living in worlds in space, and people live multi-generational in worlds in space, the idea of sending those worlds in space on 1,000-year voyages to other star systems will be no big deal because people live in space anyway. And very quickly, from where we are now to asteroid resources to people living in space, in a period of a few 100 million years, there should be life in every solar system in the galaxy. The fact that there isn't means there's a filter. The way to overcome the great filter is for humanity to move into the cosmos. And the reason that we should harness the resources of the asteroids is to make life from Earth effectively immortal, not individuals, but that we can't go extinct as a species because we have trillions of people living in the cosmos, spreading throughout the cosmos in worlds built out of asteroids. That's what the vision is that inspires the pragmatic, hard-nosed business and engineering behind TransAstra.
Marshall, you have a closing comment?
Yeah, one of my little spreadsheets that I did many years ago, I came to the conclusion that with a fertility rate of 2.9 children per woman, and you start out with about 1,000 people, 400 years after the first baby is born in space, there'll be more people in space than there is on Earth. And then about 500 years out, you are basically talking about the trillion that you just mentioned.
Exactly.
Okay, well, you approve of my spreadsheet then.
I'm not going to claim that your fertility rate numbers are that I've checked your calculations, but it's consistent with my own. By the way, if you read the work that I did on asteroid mining, on the importance of asteroid mining for the future of humanity, from 1992, I did those calculations and published it. So you might get a kick out of that paper.
You did it long before me.
Okay.
Congratulations.
All right, guys, this was fun. Thank you so much. David, I always enjoy chatting with you, and I think your new
Likewise.
Zoom format is terrific.
Thank you very much, and we'll look forward to doing it again with you down the road. Good luck, and we're watching you and hoping for great success.
Thank you.
Thanks, Joel.
Thanks. Turning off the recorder, everybody.